Thank you, David. Well, they made the mistake of giving me a microphone and a captive audience, but no piano, so apparently I'm supposed to give a talk, and we'll get into that. So, why tuberculosis? If you look around this room, you won't see very many people from countries where tuberculosis is a big problem. And perhaps that's appropriate at this stage in the development of this technology because it's still pretty expensive. But prior to the pandemic, the main application of germicidal air disinfection was tuberculosis. So, and there's a good reason for that, because these are WHO slides and not totally up to date, 2021. In non-pandemic years, tuberculosis is the number one killer of adults in the world. That's still true. 1.6 million people died from TB. Now, I think we had close to that from COVID in the United States in 1 year. That's very much an exception. Year after year after year after year for the last many hundreds of years, we have had these kinds of deaths and more. And it is, in many parts of the world, the major infection that kills people with HIV. And to make matters worse, the pandemic had a really adverse effect on global TB. There were more cases, fewer people were diagnosed and treated, death rather, and resources for TB were diverted to COVID. So situation didn't get better. Now, I'm not going to tell any more about the TB pandemic. Again, it's not tremendously relevant to this audience, except that I think manufacturers need to keep this in mind because it is the developing world is in many parts getting richer, and things that are adopted in rich countries end up being adopted in poorer countries to some degree, and the needs are a little bit different. So, as an example of how TB and UV are related, I work with the NGO called Partners in Health, and we worked in Tomsk, Siberia, and we showed back in 2007 that the major cause of multi-drug resistant TB was being admitted to the hospital with drug-susceptible TB. You went in with drug-susceptible TB, you got reinfected with drug-resistant TB, because if you went to Siberia, you would see wards of 6, 7 people, and the windows looked like they were refrigerator doors because of the temperatures. I've been there at minus 40. And so people are admitted to that ward. They have TB for sure. They don't know whether they have drug resistant or drug sensitive. And people are being admitted and discharged, and you have to fail therapy before they figure out you have drug resistant. In the meantime, you've infected some people who have drug susceptible TB. In South Africa, down here, in 2006, the world became aware of a new threat, tuberculosis that was resistant to everything we had. It's called XDR-TB, and the principal foci was a hospital. It's actually ironically called King of Scotland Hospital in KwaZulu-Natal, and very much associated with being hospitalized and having HIV. Now, does the building, does ventilation matter? This is anecdotal information, but I think it's really cool. In a medical school in Peru, in Lima, medical students start off mostly skin test negative for tuberculosis. They come from a more affluent part of the society, but by the end of 7 years, and the clinical training is the latter years, the TB infection goes up significantly from 3.5 to almost 46% of the medical students get infected with TB. Doesn't mean they get disease, but they get infected with TB. Now, it happens in that medical school that you get assigned to one of two hospitals, and they're very different hospitals. One is actually a more modern, low ceiling, smaller windows hospital, and the other is Hospital Loaiza, is a French-style hospital with big windows, and Lima is very, most of the year you can leave windows open. It's very breezy by the sea, and so if you look here, the rate of infection of the students who were admitted to this hospital, or rather worked at this hospital, was roughly twice as high as those that were assigned to this hospital. And the volume per bed was roughly twice as great in the hospital that was safer, suggesting that these big open windows and ventilation was that important a contributor to whether or not they got infected. Now, I mentioned this yesterday. For 10 years, based on these observations and what we know about TB, we at Harvard School of Public Health offered a course called Building Design and Engineering. I think you'll see Richard Vincent right here. Paul Jensen is in there somewhere. I'm in there somewhere. And this was our very first class. And for example, this architect from Pakistan, on the way home, they tore up their plans and ended up at this hospital, designed with people waiting outside. And this is Baroda, another participant, was designing for Partners in Health. And they built this hospital, built for natural ventilation, but also had UV fixtures on the wall. So again, UV for TB has fairly well established, and the importance of environmental controls. Now, there's a new problem on the horizon, and we can read about it in the high headlines this week. That's global warming, with incredible temperatures in Asia and in the US even now. And look at air conditioning sales in India, and this only goes to 2019. It's not a luxury, it's a necessity. But what do you do when you turn on the air conditioner? You must close the windows. And that is the only way of disinfecting air in many parts of the world. So manufacturers consider teaming up with split system air conditioning people and sell UV with the air conditioner. It's a natural pairing, because if you're going to compensate for the lost air disinfection that you have when you put in an air conditioner, there really aren't a lot of options. You can do a room air cleaner, or you can't do more ventilation because of the temperature issues. And so you're stuck with either room air cleaners or germicidal UV. Now, we did a little experiment, a demonstration, I would say, in South Africa with an office with 5 people in it. Had the window open, looked at the CO2 levels, they leveled off, closed the window, and in 1 hour, the CO2 levels doubled, which is to say the fraction of air that you breathe that somebody else breathed was doubled, and the risk of tuberculosis went up that much, or any airborne infection, COVID, whatever. This I wrote up in a little editorial a few years ago, and again, made the case for adding air disinfection to the mix. I've alluded to this earlier today. This is a publication from 1991 based on a study of TB in an office outside of Boston. And we used the Wells-Riley equation to look at ventilation. It was a, quote, tight office building, and 27 of 67 workers were infected over a 1-month period by a worker who came back from a vacation and had unsuspected TB. What we modeled here was that if you increase the ventilation from 15 CFM per occupant, which is sort of to 35, or 15 to 125 CFM per occupant, you get a big reduction in risk. This is infections prevented, percent of occupants. So almost 30% protection, almost 60% protection. But that protection goes down as the source strength increases. Essentially, with ventilation or with equivalent ventilation, we're removing particles and they're being added. And it's possible to exceed, the production can exceed the ability to remove them. So we don't think about that, but we should, because again, infections are generated in boluses, and we have this phenomenon of super spreaders, and so that's what concerns me about going to the lowest possible dose in terms of getting things started. Now, I wanted to show this, even though it's not strictly TB, but in Vladimir, Russia, Grigory Volchenkov and Paul Jensen, who should be here, but he's having some problems with his back, I think. At any rate, they were renovating a TB hospital, and they took one room before it was occupied and compared the cost of equivalent air changes by 3 different air conditioners. They did 3 different air cleaners, mechanical ventilation, including all of the costs associated with it, and germicidal UV. And you see here the cost per room air change and how much cheaper UV is. And these are locally made, roughly $100, probably several $100 now, fixtures that work well enough. And this is the relative efficiency of these devices. This is the air cleaner that was in one of the space capsules, so it's rather expensive. But anyway, again, highly effective, and this is upper room germicidal UV. Now, I got involved in airborne infection and TB, frankly, when I was assigned to be the TB officer, not TB, TB, in Boston in the 80s, and there was an outbreak at a homeless shelter of tuberculosis. And this is one such patient with very infectious TB. And the details of that outbreak don't matter, but as a result, I called Richard Riley at his office in Johns Hopkins and was told he just retired, but he retired to rural Massachusetts. So I was in Boston and made contact, and that began an 18-year collaboration with him in his retirement on all matters around infection, but also around germicidal UV. He's most famous for this study where in Baltimore, VA, patients were admitted to this experimental ward. All of the air was vented up to colonies of guinea pigs. Guinea pigs are exquisitely sensitive to human TB, and so it's a quantitative air sampler for TB. You can't do it with culture. It doesn't work. So this is the way you know how much TB is in the air. And he did that over a 4-year period and showed, now you'll see on the wall there's a UV fixture. They fully intended to study UV, never got to it in the 4 years they had with this facility. There were other things that required their attention. Riley, I took this picture, and Richard is holding the picture of Wells, his mentor, and who really put airborne infection on the map in this country. Later in the year or the beginning of next year, you'll see a book by Carl Zimmer, the New York Times science writer, called Airborne. And he goes in exquisite detail into the history of Wells and Riley, etc. So Riley didn't study UV in the ward, but he did do some studies in his office on a weekend. Again, not something we would get away with today. Sealed up the office and released BCG, which is a vaccine strain of tuberculosis, and with Gardner Middlebrook, famous microbiologist, had one fixture, 17-watt, very simple fixture, and looked at the efficacy. This is the disappearance rate of BCG in the room over 30 minutes. Without the fixture on, and this is with the fixture on, and that difference was equivalent to adding 10 air changes. So they figured, well, if 17-watt fixture resulted in 10 air changes, a 30-watt fixture would probably give you about 20 air changes. That sounds good. So his office was 200 square feet, and for many, many years, we used the formula of 30-watt fixture for every 200 square feet. I think we can do better than that now, and we have, but that's the history. We developed a chamber on top of Harvard School of Public Health where we could aerosolize bacteria. We've seen lots of these studies, and sample it, and did all kinds of studies in that chamber. But in 1997, I organized a symposium at the American Thoracic Society, and it happened to be in San Francisco, and invited Richard Riley and his prominent physiologist student. He had been his last mentee, Saul Permit, who was a brilliant researcher. And on a napkin at lunch, he said, "This is the experiment you should do. You need 2 chambers for guinea pigs, identical. You need patients in a ward, and you need to be able to switch between the guinea pig exposure chambers every other day. And then you can do an intervention in the rooms every other day. And these guinea pigs only exposed on days when the intervention was on. You have these guinea pigs exposed only when the intervention was off. And you'll have a perfect real world but controlled study of the efficacy of this intervention." So I carried this napkin around for a while, and every meeting I would look for people who might be interested in either funding or housing this facility, and ended up, after meeting a South African colleague at a Paris meeting of TB, setting up this facility in South Africa. And 7 years from the napkin, we've got funding mostly from USAID through CDC. Paul Jensen was very involved as an engineer. It's a TB hospital. We do have 6 beds and a corridor and a day room, patient room. All the air is vented to one of these 2 exposure chambers containing cages. We skin test the guinea pigs to find out each month whether or not they were infected. So lots of people involved. I certainly won't go through this list of people over the years, some of who are passed by now, and many of which are still involved. Now, this is a schematic of TB transmission: source, organism in the air, and into the host. And a bunch of interventions, mostly in yellow, and I think we've studied virtually every one of them in this facility that are able to be turned on and off. So we looked at masks on patients, and I'll show you that in a second. We looked at the effects of treatment. We looked at UVGI, we looked at air cleaning machine, we looked at immunization to protect the guinea pigs. The mask study I'm not going to detail because it's not relevant to our talk, but I just want to show you that the system is versatile. And so we asked patients to wear a simple surgical mask every other day, and they thought we were crazy, but they did it. And from 7 in the morning to 7 at night, and that air went to one guinea pig colony. From 7 at night to the next morning, it went to the other guinea pig colony. We did this for quite some time, and these are the results of infections over the period. So at the end of 4 months, 36 infections versus 69 in the guinea pigs, and efficacy of 53%. Probably as good a number for the efficacy of a simple mask, relevant to COVID as well, that is out there. So back to this model. So this is the basic thing. Do an intervention, and it could be UV in the upper room, and send the air to 1 or 2 guinea pig colonies. So this is one of the fixtures. We use a ceiling fan. Air came in here, 6 air changes per hour. Air went out there, close to the breathing zone, and these are the results. We had to do it in 2 phases because at the end of 4 months, we only had 9 infections in the control group, none in the intervention group, so going in the right direction, but not enough to be sure. So we continued the experiment another 3 months and seemed to have gotten a lot more infectious patients. And we had 48 more, so 57 and 15. That was a difference of rate-risk ratio of 5 approximately, about 80% effective, the equivalent of adding 24 air changes. Now we picked this dose more or less out of a hat. It was safe in terms of the occupants, but we didn't really have it. Now these were done with 2 fixtures, and I'll tell you more about that in a minute, by different manufacturers, because we didn't want one manufacturer to say, oh, here's my evidence. So 2 different manufacturers' fixtures were used, and but we did repeat the study and never published it. We should have, and Richard is giving me the evil eye because we need the second study. We used locally made fixtures and turned the dose down by 1/3 and got equivalent results. Actually, we got no infections in the treated room. So we'll put that in a letter or something to make it out there. But this is a publication of this. Shelley wrote an editorial on it, and it has been used by ASHRAE, committee that Richard chairs, as the dosing guideline. And those guidelines are that, based on the second study, actually 12 milliwatts total fixture output per volume, fixture output. So this is easy to implement. If you know the volume of your facility, you just calculate how many milliwatts of UV power, and you have to know what comes out of the fixture. The irony is, before this study, we did not really measure the output of the fixture with radiometry. When we did, we were shocked to find out that one of our fixtures with more power was putting out less UV than, and it's all in design, how good the parabolic reflector was, how good the design of the fixture was. So you need to know that. We didn't get very much into ray length, but it is another factor, and we did have good air mixing in the facility. The other number, using visual CAD program, was looking at this number, about 4 milliwatts per centimeter squared. We've been talking here about 0.1, 1, maybe 1.5 or 2, but for upper room, we had 4 milliwatts per squared, and for reasons that I'm not sure why the difference is. Now, this is the 2009 NIOSH guidelines, largely built around, largely built around Shelley Miller's chamber study, and she came up with 30 to 40 or 30 to 50 milliwatts average in the upper room. The problem with that is that how do you know what the average is going to be before you put the fixtures on? So that's why we came up with a total fixture output. So I think the basis for 222 guidance, we've heard here, oh, let's do it low, let's do it high. We have to decide how much protection we will accept. 80% good enough? Or do we want 90%? Or how much is possible? And for that we need a human transmission study, not a chamber study. And what are the safety trade-offs? And then the cost-benefit, how much you have to spend to do this. Now, I think the human-to-animal study is self-serving, obviously, but is really the answer, because we don't have, I mean, these, as you'll hear from in the next talk from Kat, that it's very difficult to do the actual epidemiologic studies. Many have tried, many have failed, including ourselves. So, but we're talking about a real-world application. This is a real hospital with a relevant pathogen. TB is a highly relevant pathogen, even though it's not a problem in the United States. Human-generated aerosol, not artificial. Particularly with 222, we need to know that it's going to penetrate that particle. We need infection as the endpoint, not particles or culture. And this facility is actually adaptable. We did convert it to human hamster SARS with the help of some manufacturers, and we're going to test fixtures. By the time we got it running, it would be difficult to get people into the hospital with it. So what I'm proposing, and we have a proposal out there, is a dose response curve for 222 with at least 3 doses and repeating one of them with a ceiling fan. The reason for do the air mixing is to compare it exactly to 254 under exactly the same conditions, and also determine with 222 how important air mixing is. We'll do shoulder level monitoring for safety and efficacy. We're going to monitor room chemistry, although with 6 air changes, we're pretty certain there's not going to be much chemistry to monitor. And we're not asking for funding for this, but Chad Roy is going to do some aerobiology as well. And we think that this too could be the basis for application guidelines. This is what we want to produce, something like this, and we can discuss what doses it would be. If Richard could convince me, we could go down to 0.1. But right now we're talking about maybe something like 2 milliwatts, microwatts rather, 1 microwatt and half a microwatt per centimeter square average room radiance. And then a ceiling fan, which we expect will increase it an unknown amount. And so I think it's the last slide. So why, I'm going to make the case for TB as the target organism we should look at, not COVID, not a virus. Why? Because there's never difficulty finding patients, and there won't be for the foreseeable future. It is intermittently susceptible. If you can kill TB, you can kill most viruses. And the Z values or K values are well established, and we've already used this it's being used for ASHRAE. This is where TB sits on the relative to ordinary bacteria and fungi is right in the middle in terms of Z values. And that,